Hello, today we are going to introduce a 3D printed sweat collector. Ecrin Sweat is an attractive class of biofluid suitable for the non-invasive monitoring of body chemistry. Sweat contains a rich composition of biomarkers relevant to physiological health status, including electrolytes, metabolites, hormones, proteins, and exogenous agents. Studies demonstrate the intermittent or continuous assessment of these and other sweat biomarkers offer time dynamic insight into the metabolic processes of the body, relevant to applications ranging from athletic performance to medical diagnostics. Recent advances in soft microfluidics, sensing technologies, and electronics establish the foundations for a unique class of skin-like epidermal microfluidic systems. Adapting concepts from traditional lab-on-chip technologies, these wearable microfluidic platforms comprise of sophisticated networks of channels, valves, and reservoirs embedded in elastomeric substrates. The thin, flexible device construct facilitates a conformal fluid-tight skin interface by virtue of skin-compatible adhesives to collect sweat directly from sweat glands. The integration of colorimetric, fluorometric, and electrochemical measurement techniques enables such platforms to measure sweat constituents in situ across a wide array of applications and environments. Traditional approaches for sweat collection use absorbent pads or microbore tubes pressed against the epidermis by virtue of bands or straps to capture sweat as it emerges from the skin. Requiring trained personnel, special handling, and costly laboratory equipment, such methods are incompatible with real-time sweat analysis and prone to sample contamination or loss. Epifluidic devices eliminate external sample contamination by virtue of the intrinsic encapsulation of the microfluidic network and conformal skin interface. Such systems are vulnerable to surface contamination from exogenous agents present on the epidermis, such as cosmetics or natural oils, without careful preparation of the skin surface before device attachment. Furthermore, the dependence on an adhesive interface for skin attachment limits these devices to single-use applications. Upon removal, the risk of contamination, potential sample loss, and active sweat response of previous covered glands pose substantial challenges to reapplication and continued sweat collection. The typical epifluidic fabrication pathway uses soft lithography techniques to produce devices with microfluidic components and complex geometries. A common, well-established process for fabricating lab-on-chip microfluidic devices, soft lithography, requires high-precision molds to form discrete patterned layers of an elastomeric material, for example polydimethylsiloxane or PDMS, that when bonded together yield a sealed device. Traditionally, producing molds with sufficient feature resolution, under 20 micrometers, requires expensive, time-consuming processing methods, micromachining and micromilling, and access to specialized environments, a clean room. Such requirements result in elongated device design cycles, inequitable access to equipment necessary for innovation, and additional challenges for commercial deployment due to incompatibilities with large-scale manufacturing. Additive manufacturing, AM, or three-dimensional 3D printing represents an attractive alternative to conventional planar 2D fabrication methods. AM offers powerful capabilities for producing structurally complex objects with true 3D architectures through a rapidly expanding library of printing methods. In general, these methods create solid objects in a sequential, layer-by-layer manner directly from a digital computer-aided design or CAD file. In the context of microfluidics, the use of 3D printing is well established for the rapid, cost-effective fabrication of high-resolution templates for soft lithography. In particular, that photopolymerization techniques, for example resin-based printing, stereolithography, digital light processing or DLP, and continuous liquid interface polymerization enable rapid production of microscale features under 100 micrometers over large areas under 600 micrometers squared with high precision. Innovations in printer hardware, software processing, and materials chemistry further extend these 3D printing capabilities to enable the direct production of enclosed microfluidic channels for lab-on-chip applications. Although manufacturers advertise printers with high resolution, XY resolution under 50 micrometers, and Z resolution under 5 micrometers, in practice, the obtainable channel dimensions and device complexity are typically limited to millifluidic features under 250 micrometers. Printer specifications represent only one key constraint to printing devices with micron-scale internal fluidic features under 100 micrometers. Successful fabrication requires optimization of other critical factors, including printing technology, feature design and spatial location, and printer-dependent parameters. AM process optimization, particularly for vat photopolymerization, demands careful attention to the chemistry of printed materials. Resin formulations must simultaneously satisfy application-specific requirements such as biocompatibility or optical clarity, while preserving printability. Recent reports leverage specialized DLP-based printers and customized resins to fabricate devices containing microfluidic components with under 50 micrometer dimensions. In general, wearable system designs must address the inherent mismatch between the mechanical properties of skin and rigid planar device components. The most advanced platforms fabricated by conventional non-AM methods exploit sophisticated strategies, combining complex device geometries and soft, low-modulus materials to establish a seamless, non-irritating epidermal interface. Recent advances in soft material chemistry support 3D printing approaches to fabricating wearable devices for applications spanning biophysical, biochemical, and environmental monitoring. However, such capabilities remain limited for the 3D fabrication of epifluidic devices as a result of the high Young's moduli of the primary material chemistries, for example, methacrylate-based resins, suitable for printing high-resolution microfluidics. Current efforts to fabricate skin-interfaced 3D printed microfluidics use alternative printing methods, for example, fused deposition modeling and direct ink writing, that support fabrication with low modulus materials at the expense of printer resolution, under 200 micrometers. In the context of epifluidics, the ideal fabrication scheme would use resin-based printing to fabricate devices with feature sizes comparable to conventional methods, with biologically compliant form factors. Such an approach would transform the fluidic design space with truly 3D device architectures while enabling a rapid, iterative design process, facilitating individual specific device customization and reducing the cost for low-volume production. This paper introduces a set of strategies, processing approaches, and microfluidic designs that support such fabrication techniques using a commercial DLP 3D printer and a simple manner of operation. A modular 3D printed epifluidic platform, termed a sweatainer, demonstrates several unique aspects of an AM approach to fabricating epifluidic systems. This platform, to our knowledge, represents the first 3D printed epifluidic platform with true microfluidic dimensions. Specifically, the results highlight the potential of a true 3D design space for microfluidics through the fabrication of fluidic components, channels, and valves with previously inaccessible complex architectures. Printer optimization strategies and systematic experiments enable realization of micron-scale feature sizes under 100 micrometers and enhancement of optical transparency of 3D printed channels. In combination, these concepts support integration of colorimetric assays to facilitate in situ biomarker analysis operating in a mode analogous to traditional epifluidic systems. Drawing inspiration from the Vacutainer blood collection tube, the sweatainer system introduces a novel mode of sweat collection, termed multi-draw. This method overcomes the inherent limitations of single-use devices by enabling the collection of multiple, independent, pristine sweat samples during a single collection period. Field studies of the sweatainer system demonstrate the practical potential of these concepts. Thank you for watching.